spacecraft launcher named for robot in Interstellar could help us reach another star system. Here's how. Reaching interstellar space could be far simpler than we thought, thanks to a new idea called TARS, or Torqued Accelerator using radiation from the sun. It's essentially a solar-powered centrifuge that can slingshot tiny probes to speeds greater than the escape velocity required to exit the solar system. Undertaking an interstellar mission is one of the most challenging problems that humanity is ever going to face. David Kipping, the scientist behind the idea for TARS, told Space.com, TARS, named after the robot from the 2014 film Interstellar, could potentially be a way to travel to other stars. TARS requires no fusion reactors, no gigawatt laser, and not even a chemical rocket, other than to launch TARS from Earth. Instead, the beauty of TARS lies in its simplicity. Here's how it's meant to work. Kipping, who is professor of astronomy at Columbia University in New York, envisaged TARS as featuring two paddles, with each paddle having reflective coating on one side and a dark coating on the other. The paddles would be situated 180 degrees with relation to one another, so the reflective sides point in opposite directions. They would be connected by a tether. Like with a solar sail, sunlight would push on the reflective sides, causing TARS to spin, faster and faster until it reaches a critical velocity at which a tiny spacecraft, perhaps no larger than a mobile phone, is flung off at high speed. TARS would also act a bit like a battery, charging up with solar energy until it's ready to release all that solar energy as kinetic energy. In his paper, written with Columbia engineering student Catherine Lampo, Kipping gives an example of two paddles just 2.8 microns thick but 23 feet or 7 meters wide, separated by a tether 207 feet long or 63 meters, that can be spun up for 3 years before slinging its tiny spacecraft away at 7.5 miles or 12.1 kilometers per second. Add its orbital motion to its slingshot speed, and this device should get above the 26 miles or 42 kilometers required to escape the solar system and enter interstellar space. Traveling at that final speed, however, would take over 30,000 years to reach Alpha Centauri, which is 4.3 light years away. On the bright side, there are things that can be done to speed things up even further. In terms of the basic design, Kipping says there are two factors that govern the release velocity. One is how long you charge it for, but the most important is the specific tensile strength, which is the tensile strength relative to the mass. Tensile strength describes the maximum load a material can carry before breaking, and it is determined by the material used. The strongest off-the-shelf materials Kipping could find were commercially available sheets of carbon nanotubes, which is what the calculations in his paper are based on. However, in the future, we might find a way to manufacture graphene at an industrial scale, which would be a much better material because it has a much greater tensile strength than even carbon nanotubes. This would significantly improve the release velocity, Kipping says. Other techniques could include harnessing the Obert effect, whereby a spacecraft accelerates as it moves towards the sun, so when the sun's gravity slingshots it away, the spacecraft's velocity is increased. On that end, though, there's a problem. Gradually, the impact of solar radiation would start to push TARS away from the sun, and the farther it gets from the sun, the less sunlight it receives. Sunlight drops off following the inverse square law, so at twice the distance from the sun, TARS would feel 4 times less sunlight. Kipping has a solution ready. It's called a quasite. It's a variation on an idea called a statite, which is a kind of solar sail, except it is designed so the outward pressure from sunlight is perfectly balanced with the inward pressure of the sun's gravity. A statite solar sail, therefore, doesn't actually sail anywhere. In comparison, a quasite would be slightly unbalanced, feeling a little more gravity than it does outward radiation pressure, causing it to fall towards the sun. Give it a little nudge sideways, however, it can keep in an orbit around the sun, similar to how satellites are in free fall about the Earth, always falling under Earth's gravity, but on a trajectory that follows the curve of Earth. For a quasite, gravity still wins, so it wants to fall into the sun, and so you need a bit of motion to keep it in an orbit, but that orbit would be very slow. This is what makes a quasite stand out. It doesn't follow Johannes Kepler's laws of orbital motion. For example, Mercury's orbital velocity is much faster than Earth's because it's much closer to the Sun. A quasite, on the other hand, could orbit the Sun at the same distance as Mercury, but with the slower pace of Earth. Being a quasite would prevent TARS from being pushed away from the Sun, allowing TARS to maintain its distance and maximize the amount of solar energy it receives. Although in theory there is no maximum speed limit, the design would need to grow exponentially in size if trying to reach relativistic velocities that are a significant fraction of the speed of light. In reality, by combining quasites with the Obert effect, graphene construction, an electromagnetic field, and something to initially spin TARS up, such as a laser, a tiny spacecraft released from TARS could reach a velocity of up to 620 miles per second or 1,000 kilometers per second. That is 0.3% of the speed of light. Moving at that final velocity, a spacecraft could reach the Alpha Centauri system in just under 1,300 years. People always say you're never going to reach Alpha Centauri in your lifetime, but in a way, who cares? To me, it seems very selfish to insist that any space system we build has to reach its entire completion cycle in a human lifetime. What we're trying to do is leave a better world for the people that come after us. And this task of going interstellar and exploring the universe, it's a progressive, multi-generational activity. As long as we can get there, get photos, and get them back, then it's worth doing. TARS is, of course, still only a paper concept right now, but Kipping has revealed that he has received interest from some private spaceflight companies offering space on their next launch for free if he can supply a CubeSat-sized prototype of TARS. He's had to take a rain check on that, as we don't have anything to launch. Maybe in the future we can take them up on that offer. I do think it's the kind of project that undergraduate students could build. The concept that an undergraduate student could help build an interstellar mission is an amazing one, but that is the potential that Kipping sees in TARS. The key engineering difficulties for a prototype would be in its deployment, unfurling micron-thick panels and then getting telemetry down to Earth so the team could make sure it is spinning correctly and not tumbling. The fewer moving parts and the simpler the design, the better. Indeed, Kipping has modified his own original design, removing the tether and joining the paddles in a single structure, tapered on either side. People say, why not wait 300 years until someone invents a warp drive? I say, why not get started now, because there's no guarantee of that happening, and generations down the line will reap the benefits of our investment. As Kipping said, we just need all the ideas we can get. The more options we have on the menu, maybe some combination of them will get us to the stars. Thanks for tuning in. Make sure to subscribe to our YouTube channel for the latest science and tech news and other captivating content.